In this video we're going to look at what is called the total differential. The notation for it is dP, and we're going to contrast that with a change in P being pressure, which we would designate as delta P. The significance of these two different entities is that delta P is the exact change in pressure, and dP is the approximate change in pressure. So dP is kind of a shortcut way to get a change in pressure that we may need sometimes. So let's define our function P, pressure, to be a function of temperature and volume. And let's show what delta P would be. It would be the pressure at a time change and a volume change minus the original pressure. So the pressure at a change in time and a change in volume minus the original pressure. Let's rewrite delta P in this way below, in the line below. So what we have done here is we've done something that is similar to what you do in the proof of the product rule in Calculus 1. We have subtracted and added the same thing, so that when we subtract and add those two expressions, they come out to be 0. And we have expressed this single difference as two differences, as this difference added to this difference. And in the first case we have divided and multiplied by delta T, and in the second case we have divided and multiplied by delta V. So take a look at these, at the expression on this line, and satisfy yourself that it is the same as the expression on this line right here. We subtracted this, added this, and those are the same as 0. We've divided and multiplied by the same thing, so we multiplied by 1, and we've divided and multiplied by the same thing here and here, so we multiplied by 1. And now what we want to do in both of these expressions is take a limit. So in the first expression we're going to take the limit as delta T goes to 0, and in the second expression we are going to take the limit as delta V goes to 0. So what does that give us? Remember how we defined the partial derivative. The partial derivative was the change in only one of the two variables. So here in this first expression we are changing only T. It's T plus delta T and T, whereas we are not changing V. Whereas in the second expression we are changing V, but we are not changing T. So it should make sense that the first expression, the first expression's limit would be delta partial P with respect to the change variable T, and the second one would be partial P partial V. The thing that we need to also note, though, is that we've got this extra delta T here and this extra delta V here, so we have to multiply this by dV, and we have to multiply this by we have to multiply the first one by dt and the second one by dV. So let's pick that up on the next blackboard. So we get this. Let's take a look back, though. We took the limit as T goes to 0 and as V goes to 0, so we were altering delta P, and we were altering delta P to turn it into dP. the total differential, or what is called the total differential, and that was the limit of this expression, which gave us this, and the limit of this second expression, which gave us this, and this is where we are for the total differential. So remember, we start off with delta p, and we took its limit and got a dp. Delta p was the exact change, and dp is going to be the approximate change. And so let's go through an example where we find the exact change in pressure as well as the approximate change in pressure, and see that they are, if we don't need a great deal of accuracy, can be made very close together. So let's start with delta P being P of T plus delta T, V plus delta V minus P of TV. Remember that pressure, or in this case we're going to define pressure as RT over V, and instead of using delta P in this form, we're going to calculate delta P as R second temperature divided by second volume minus R times initial temperature over initial volume. So let's plug in the numbers in example 12-3, and we get this. So we've factored out R, and here are our T2 and our V2, and here are our T1 over our V1. And if we simplify, we get this. We get 3 joules per liter as our delta P. So now we're going to calculate the total differential, our approximate change in pressure. Remember that our pressure was we're defining pressure as RT over V, so partial P partial T is going to hold R and V constant and give us just R over V, whereas partial P partial V, we should rewrite pressure as RT V to the minus 1, where this part is a constant, so partial P partial V would be minus RT times V to the minus 2, or minus RT over V squared. So plugging that in to our dP equation, we get this. And then we can just plug in all of the known quantities. So R was 8.314, and we get this. So just going through what we're plugging in, here's R, 8.3144 joules per Kelvin mole. The volume is 10 liters per mole. The change in temperature is 0.85 degrees Kelvin. And then in the second term, we have R again. The volume, 10 liters per mole, is squared, and the change in volume is negative 0.1 liters per mole. So if we do all the computations and unit analysis, we get this. We get the same thing that we got before, to two significant figures. So the delta P and the dP, the difference between the exact and the approximate, they are essentially the same, or they are the same to two significant figures in this case. So in the second part of this video, we're going to look at the chain rule for functions of two variables. We actually have two variables for the function u, and in addition to that, we have x has an inside variable t, and y has an inside variable t. Sometimes we call that inside variable t here and here a parameter. So what we're trying to get here is the derivative of u with respect to t and to get the derivative of u with respect to t, we are taking the derivative of f with respect to t, but f has two variables inside, so the chain rule says this. First we take the partial of f with respect to x, and then multiply that by dx, and then we take the partial of f with respect to y, and then multiply that by dy, and we add those two together. So it should look very much like the regular chain rule: derivative of the outside, derivative of the inside, and again derivative of the outside, derivative of the inside multiplied together in both those cases. But why we add those two together, we'd have to go to the limit definition of the derivative to show that. Right, so we would, in taking the derivative with respect to t, we would alter both the x variable and the y variable by h, and then not like a partial one, we're only varying one variable, we're varying both the x and the y variable, and then we would have to split it up like this. So if you look at this next blackboard, what we're doing to calculate these this du dt here, let's see, we actually are splitting it up into the sum of two derivatives, or two limits. You can see that we are subtracting and adding the same thing, so that really we just have this minus this. But it gets pretty complicated, right? Because not only are we splitting it up into two terms, but to get the inside variable t in there, we're dividing by this and multiplying by this, dividing by this, multiplying by this. But perhaps you can see that this part right here is going to go to partial f partial x, and this part right here is going to go to x prime of t, and this part right here is going to go to partial f partial y, and this part right here to y prime of t. So back to the previous slide, that's why we get what we have here. So if we define the function u as x squared y plus xy squared, and we define the function x as t e to the minus t, and the function y as e to the minus t, and we plug into the du dt formula that we have here, let's see what we get. So using this chain rule formula that we have developed here for du dt, we're going to apply it to this function u, a function of x and y, and with x being a function of t and y being a function of t. So let's calculate the partials and the derivatives that we need. So first we're calculating partial f partial x of the function u, and so that's going to be holding y constant, so we get 2xy for the partial of the first term, and then for the partial of the second term we get y squared, because the partial x with respect to x is 1, and then we just bring down the constant y squared. And now we're going to take partial f partial y, and that is going to be, we're holding x constant, so the x squared acts like a constant. Partial y of the y is 1, and in this second term right here, the x acts like a constant, and the partial of the y squared is 2y, so we get 2xy. Now we need to go back and find dx and dy, and we're going to put those here and here. So dx is the derivative with respect to t, product rule here, so it's minus t e to the minus t plus e to the minus t. So that is, when we combine terms, 1 minus t e to the minus t. And then we're taking the derivative of y with respect to t, so dy is minus e to the minus t. So let's put those in here and here in the dx and the dy position. So here they are right here and here. Now the next thing that we need to do is we need to take this expression here and this expression here, which are in terms of x and y, and we need to transform them into the variable t using the fact that x equals this and y equals this. So we're going to do that on the next blackboard. So we have where we left off on the previous page rewritten up here, and now let's substitute in x equals this and y equals this. So everything is substituted in on these two lines, and now we want to collect terms. And so let's note that in this first term we have in in this first parenthesis e to the minus t times e to the minus t appearing here and here, so that is e to the minus 2t, and that is multiplied by e to the minus t. So that means we can factor from that term e to the minus 3t. That also turns out to be something we can factor from this second term, because there's an e to the minus t times e to the minus t here, e to the minus t times e to the minus t here, and that expression is also multiplied by e to the minus t. So we're going to be able to factor out e to the minus 3t from both terms. When we do that, we get a 2t plus 1 from here. We get a 1 minus t from here. We get a t squared from here, a 2t from here, and a minus 1 from here. Select the t squared terms, which are minus 3t squared, and the t terms, which are here and here and here, so that's minus t, and there's only one constant term right here, a plus 1. So that gives us e to the minus 3t multiplied by minus 3t squared minus t plus 1. So that's the result of this du dt problem. And that concludes this video with this result.